So here's the third example that I left you as an exercise. Anybody who have tried this one, can you share the answer, whether it is rejecting H0 or failing to reject H0? Anybody who has tried this example? What is the decision? No one tried it? So homework is homework, right? Okay, so I get an example. I failed to reject H0 with test statistic 1.574. Okay, so that's correct. Any other answers? Failed to reject H0. Okay. What is the degrees of freedom for this test? What is the degrees of freedom for this test? $19. Okay, that's right. So here's how we can do it. So the question says the researcher claims that the mean weight of group of students is 132 lb. These are in pounds, not in kilograms. Okay. Can you conclude at 1% significant level? Now your alpha is 1%. Okay. So the mean weight differs from 132 using a sample of 20 students. And you know the sample mean, which is x bar, and the sample standard deviation is S, so 14.2. And the sample size is 20. So the first thing, what is it? What is the case? First case, second case, or the third case? You do not know sigma, but you know is the sample standard deviation. So sigma is unknown. Then you look at the sample size, it is 20. It is small. So this is the third case. So you have to go for the t-test, right? So you have to go for the t-test. Okay, right. So let's start with writing the hypothesis. H0 and HA. So what is it saying? A researcher claims that the mean weight is 132. What do you want to conclude? Can you conclude that it differs from 132? Differ, that means not equal. Okay, so differs is not equal. So we start writing HA. Mean is not equal to 132. So this is mean equals 132. So this is going to be a two-sided test. How do you decide the side of the test? Which hypothesis are you checking to test or to identify the side of the test? H0 or HA? Yes, how do you decide the side of the test? Looking at H0 or HA, which one? Yes, we have to look at the HA. Okay, so what is the rule for H0? I mentioned there's a certain speciality that you have to remember when you are writing H0. What is that? H0 always contains the equal sign. Thanks, Sahara. So that's the rule. The side of the test is decided by the alternative hypothesis, and the equal sign always goes to the null hypothesis. So what you want to conclude should go with HA, okay, and someone else's claim, the one that you want to reject, should go to H0, right? So H0 and HA are the complements or the opposites of each other. Right, now we have a two-sided test and it is about the mean. So I have completed the first step, writing the hypothesis. The next is finding the test statistic. Since this is the third case, you will end up with the T test statistic, T score. So what is the equation? X bar minus mu naught divided by S over square root of n. X bar is the value you see in your sample mean, it's 137. Mu naught is what you see under the claim, H naught, that is 132, divided by S is given 14.2, divided by the square root of 20. Right, so that will give you a T score, and that was, I think I got the answer. What was it? 1 point? We had 1.5738, 1.57. Let's see. Okay. So 1.574. Right. So that is the test statistic. Now, what is the next step? You have to go for a and you have to go and find the rejection region. Right. Now, since this is a two-sided test, you'll have rejection region on both sides of your T table or T curve. Right. And what is the alpha value? It says that alpha is 1%, right? So if alpha is 1%, you have to divide it by 2 because it's two-sided test. So you'll end up with 0.005 or 0.5%, which is each tail should contain 0.005, right? Okay, so we need this cutoff value, right? We need the cutoff value from the T table with the degrees of freedom n minus 1, n is 20, so the degrees of freedom will be 20 minus 1, which is 19. Right, so let's look at the T table. For your tail should be one tail is 0.005 with the degrees of freedom 19. So that will be 2.861, right? 2.861, yes. So you have, can you see that? You have a single tail should contain 0.005 here. Okay, so both tails together it is 1%. So 1% is actually 1% significant level is actually the 99% confidence interval. So you can choose anyway. It's the same column, and the degrees of freedom is 19. So you have 2.861. Right. So let's use that as our boundary for the rejection region. So that will be plus or minus by symmetry 2.861. 2.861 plus or minus. So here's your rejection region. The colored area is the rejection region. So what is the next step? Last step, you go back and take your test statistic and place it on your graph. So here's 1.574. The positive value less than 2.861. So where is it? It is in the non-rejection region. So the test statistic is in the non-rejection region. So what is your decision? We fail to reject H naught. Right, so we fail to reject H naught. So can you write the conclusion? Right, how do you write the conclusion? The conclusion is we So we fail to reject H0. That means we are unable to conclude what we wanted. So we say we do not have enough evidence to conclude that. We do not have sufficient evidence to conclude that. What do we want to conclude? The average weight, right? Average weight of students differs from 132 lb. We wanted to conclude it, but we do not have sufficient evidence to conclude it at 1% significant level, right? So that is our conclusion. Okay. Now, there's another way that you can check your answer. There's another way. That is based on the confidence interval. Okay, so the confidence intervals and hypothesis testing, they actually go together. Both of them will give you the same conclusion actually. Okay, so sometimes now the confidence intervals can be used with only the two-sided test. Otherwise, you have to go for the confidence limits, the upper limit or the lower limit. In this course, we'll only go with the confidence interval since that's what we covered in last chapter. When you have two-sided test, you can double check your answer with the corresponding confidence interval. The corresponding confidence interval. Okay, so what is the corresponding confidence interval? If your significant level alpha is 1%, okay, if alpha is 1%, what is the corresponding confidence level? The rest of it, that is 100 minus 1, which is 99%, right? So this is to check using the corresponding confidence interval, because you can't use any confidence level. Okay, since alpha is 1%, right, the confidence level will be 99%. Okay, so if you construct the 99% confidence interval for this sample, okay, let's see what will happen. Okay, so let's construct the 99% confidence interval for the mean. Can you remember how we did the confidence intervals? You get the point estimate plus or minus the margin of error. And how do you find the margin of error? So your point estimate is what? Point estimate is always the, if it is about the mean, your point estimate will be x bar plus or minus. Your margin of error is, since this is the third case, it will be the t-score with the corresponding degrees of freedom times the standard error, right? So this is how you construct the confidence interval for the third case. If it is the first case or the second case, you have the z-score with sigma over square root of n or s over square root of n if sample size is large enough. If it is the third case, you go for the t value, right? So t-score, now this t-score for 99% confidence, for degrees of freedom 19, you already have that t-score. See, it's in your rejection region. So this is the same thing, right? It's the same thing, right? So if you look at the 99% confidence interval, the t table, that's I showed you a little while ago. For 99% confidence interval with 19 degrees of freedom, you have this 2.861. So that is the t-score. Now what is x bar? X bar is 137. So let's find the confidence interval. 137 plus or minus 2.861. And what is S? S is 14.2 divided by square root of 20. Can you find this confidence interval? Tell me what is the upper limit and the lower limit? So I have the margin of error to be 9.084. Let me know if I have made any mistake. See whether you can get the same value. So that is my lower limit. And the upper limit. Is this correct? My margin of error? Can you please double check? Can you all get the same answer? Right. Okay. Now, how can we double check this one, right? So you have your corresponding confidence interval, 127.916 up to 146.084. So what are we going to do now is, what we have to do is, you go and look at the value that you see under the hypothesis, H0. What is the value? 132. Now check whether 132 is included in this interval or not. What do you say? Is 132 included in this interval? It is from 127 up to 146. So obviously 132 is inside this interval. So that is why we cannot reject that claim. Okay, the claim says the mean weight is 132. When we construct the 99% confidence interval, 132 is inside it. So we cannot say it is not at 99% confidence interval, right? So therefore, we can write that since this mu naught, which is 132, is included in the interval, we fail to reject H naught. We can't say it is no. Right? We fail to reject it. Right? So that is how you, so see, you got the same, the conclusion, you fail to reject H naught. Right? From the two-sided hypothesis test also, you fail to reject H naught. Right? Now, what if in another example, your hypothesis, the hypothesized mean is not inside this interval, it is outside, maybe to the left, maybe to the right. If it is not included inside the interval, then you reject it, right? So you can reject H naught. So you'll get the same conclusion from the hypothesis test and also from the corresponding confidence interval. Now, if you do the hypothesis at 5% alpha, what is the corresponding confidence interval? If alpha is 5%, the corresponding confidence interval will be 95%. If you do the hypothesis at 10% alpha, the corresponding confidence interval will be 90%, right? So you'll end up with the same cutoff value. If it is case 1 or 2, it will be the Z score. If it is case 3, it will be the T score. That you see these two T scores, the plus or minus values in your rejection region boundaries. So what do we call them? The critical value, right? Can you remember? We call them the critical value. So that critical value is actually the value you use in your confidence interval, the T score, the Z score, right? And then look at the confidence interval and check whether H naught, not the mean, okay, not this sample mean. You check whether H naught, whether the mean that you see and H naught, which is mu naught, is included in the interval or not. If it is included, then you can't reject it. If it is not included, if it is outside the interval, then you can reject it, right? So that is another way to double check your hypothesis test answer. This can be done only for two-sided test. For one-sided test, you have to go for confidence limits, upper limit or the lower limit. I'll show that when we do practical session. Okay, This is the same thing actually, right? So you'll see the same thing. Okay. So far for hypothesis testing, we use this rejection region approach, okay, or we call it the critical value approach, okay. So there are two approaches actually. I mentioned it earlier also. There are two approaches you can use to make the decision. One is called the critical value approach. That is what we learned. Okay, the critical value approach. And the other one is called the p-value approach. Okay. If you use a statistical software, you will use this p-value approach, because when you do a certain hypothesis test using a statistical software, the output will give you this p-value, okay, or a probability value. So based on the probability value, you can easily make your conclusion whether you reject H0 or not, okay. And the p-value approach is possible when you have z-score, because with the t-score in the t-table, you do not have all possible probabilities, right? The t-value is different from the z-table. In the standard normal distribution for any z-score, you can find a probability from the table. But the t-table, it's different. What you have are the selected t-scores for selected tail probabilities. Okay, so therefore the p-value approach is not possible if you do hand calculation with the t-score, but when you use the software, p-value approach is the one we use. Okay, so I'll explain the p-value approach using the example we did for a proportion. Okay, so I'm going to go back. Right here. First, I'll explain how to get the p-value, right? P stands for probability. So this is how you find the p-value. If you have a right side test, after you find the test statistic, okay, rather than finding the rejection region, what you do is you get the test statistic, the z-score, and read the z-table and find this tail probability. This is called your p-value. Okay, if it is a right-sided test, usually you'll end up with a positive test statistic, and anything above the right tail, anything anything beyond the right side of the test statistic, which is that probability is called the p-value. Okay, when you have a z-score, you can read the standard normal table and find this p-value, right? If it is a left tail test, you find, you place your test statistic on the standard normal table. Now, most often the test statistic will be a negative value. Anything to the left of that test statistic, which is called the p-value. Okay. If you have a two-sided test, what you do is whatever the test statistic you have, it can be positive or negative, you have to take both tails. Okay, whatever the positive or negative test statistic, if you take both of them, and your p-value will be, let's say this is the probability of the left tail and this is the probability of the right tail, because of the symmetry, p1 and p2 are same, right? So your p-value, so I just write p here, your p-value will be 2 times p. You add the left tail p-value and the right tail p-value. They are going to be same because of the symmetry. So your p-value will be 2 times the tail probability. Okay. Now, after you find the p-value, now remember the steps now. You write the hypothesis, you find the test statistic, and then using the test statistic, you find the p-value. Okay, that is the tail probability. If it is right-sided test, you get the right tail probability. If it is a left tail test, you get the left tail probability. If it is a two-sided test, you take the tail probabilities of both sides, add them together. Now you have something called the p-value. Then how do you make the decision? You compare your p-value with the alpha level. Right now, this is where you use the alpha. Your alpha value will be 1%, 5%, or 10%. So what do? you compare your p-value you got from the previous step with the given alpha value. If the p-value is small than the alpha, you reject H naught. Just remember this one. If it is greater, obviously it is failing to reject H naught. Okay, so just remember only one side or one condition. If the p-value is less than alpha, what does that mean? The p-value is less than alpha means your alpha is your alpha value is again the probability, say 5% is 0.05. So that 0.05 probability is somewhere covering all these areas. So this is your critical value. That means your test statistic is in the rejection region. So it's the same thing doing in a different way, right? So using the p-value approach, what you do is after you find in the p-value, you compare it with alpha. If it is less than alpha, you reject H naught, else you fail to reject H naught. The rest is the same when you write the conclusion, depending on rejecting or failing to reject H naught, you simply write the conclusion as you did in the previous examples. Okay. Now, if you use a software, if you look at the computer output, it will give you both test statistic and the p-value. So it is very easy. You can simply get the p-value and compare it with whatever the alpha value you want. And then you can either reject H naught or fail to reject H naught. Okay. Now, shall we go back to that? Is this clear to all of you? Any question? Okay. So let's go back to that example. Right, so we have a question, should the sample size be 20, less than 24 or 30 to get 3? Now, there's no exact rule as 25 or 30. If you refer several textbooks, some people use 25, some authors use 30. So in this course, we'll stick with 30, okay? We'll stick with 30 because if you refer several textbooks, you will see the variation, 25 and 30. Some even go for 35, right? So I cannot say this is the exact value. In this course, we'll stick with 30 as the cutoff, okay? So if you see your sample size less than 30, consider it as a small sample, okay? So I'm going to go back to the proportions, right? Now let's look at the very first example we did, which was a right-sided test, okay? Now look at the steps. We wrote the hypothesis, the test statistic, and after you find the test statistic, what should you do now? You have to find the p-value correspond to this 2.32. Okay, so rather than finding the rejection region, so I'll write it separately here. Okay, p-value approach. Right. So what do? You take the test statistic 2.32. This is a right side test. Here's my bell. 2.23, 2.32 is somewhere here. So where's the p-value? Everything to the right of this. Now, do you have the Z table with you? So anybody who has the Z table with you, I'll try to download it, okay, until you read it. Okay, so give me a minute to load it to the shared screen. Okay, so you got the p-value from the, sorry, the the probability to the left tail of your z-score, right, which is 0.98983. But what is your p-value? It is the right tail, right? Your right tail is 1 minus 0.98983. Yes, so what is your p-value? The p-value will be 0.01017. Okay, is this clear to all of you, how to get the p-value now? Okay, so here's your p-value. So what is the last step?
Madam.
Yes.
Excuse me, madam.
Yes.
Madam, can you explain it again?
To how to get the p-value? Yes. Okay. So your when you do the hypothesis testing, you found the test statistic. Okay, the 2.32. That you know how to find it using the equation. After you find the 2.32, rather than finding the rejection region based on alpha, what we do is we read the Z table. Okay, we read the Z table for 2.32. This is a right-sided test. So your p-value will be in the right tail. Okay, the p-value will be in the right tail because it is a right-sided test. And the p-value, you find the p-value right to the test statistic, which is 2.32. Okay, so I'll show you the Z table. Here's the Z table. 2.32, here's 2.3, and the second decimal place 2. Right? So you have 2.32 is 0.98983. And remember, when you read the Z table, it's always giving you the left tail probability. For the Z score 2.32, your left tail probability is 0.98983. But what we want is the right tail, right? Your p-value is the right tail. So you do 1 minus 0.98983. Okay? So let's go back to the question. So 1 minus 0.98983 is 0.0117. So that is the p-value for your hypothesis test. Now what is the next step? You have to make the decision. So how do you make the decision? You compare this p-value with your alpha. Now this is when your alpha is going to play the role. So what is the alpha? 5%. Right? What is the alpha? 5%, 0.05. And here's the p-value. Now what do you say? 0.0101, is it less than or greater than alpha? 0.01, is it less than or greater than 0.05? What is the sign you put? Less than or greater than? Yes, you see it is less than, right? So what is the rule? If the p-value is less than alpha, you reject H0. That is the rule. If the p-value is less than alpha, you reject H0. See, you have the same answer, right? So it is up to you when you do the hypothesis using the hand calculation. You can either use the rejection region approach or the p-value approach. When you have the Z scores, okay, with the T score, it is hard to do the p-value approach because we do not have the exact probabilities in T table. But for proportions, all three cases, all the time, the test statistic is a Z score. Therefore, you can use either rejection region approach or p-value approach. But if it is the mean, only for case 1 and case 2, you will end up with Z scores. In those situations, you can go for p-value approach. But if you are using a computer output to make your decision, it will be always the p-value. The p-value will be displayed on your output. Your p-value is this, right? So you pick it and make your conclusion, right? So we'll do examples using how to read the computer output also later when we do the lab session. Okay, shall we try another one? Okay, let's do the left tail test also. Right? In the left tail test, okay, so in the left tail test also, so I'm going the p-value approach. Okay, so I have already uploaded this document to your LMS. But since I did some changes with the p-value and everything, I'm going to remove the one which is already there and replace it with this one at the end of the lesson today. Okay, so you'll have all the extra things I wrote on this file. Okay, so let's do the p-value approach, right? So how do you do that? You have the test statistic. Rather than finding a rejection region, you are going to find the p-value. How do you do that? This is a left tail test. So the p-value will be in your left tail. See, you have a negative Z score, negative 1.265. So with the rounding, let's go 1.27. Okay. This should be your p-value because it is a left tail test. Anything beyond negative 1.27, that probability or area of this left tail is your p-value. Shall we read the table? Negative 1.27. Yes, the table. Negative 1.2 is here. 1.2 and 7 is here. Right? The negative 1.27 is 0.10204. 0.10204. Okay? 0.10204. So let's write it in our document. Okay. For negative 1.27, it is negative 10204. So that is the p-value. Now you have the p-value, compare it with your alpha, right? So let's go back and get the alpha. Alpha is at 5%. Okay. This p-value is 0.10204 and alpha is 0.05. Now what is the sign? P-value bigger than or smaller than? Now if you look at this p-value, it is greater than the alpha. So what is your conclusion? If p-value is less than alpha, you reject H0, else you fail to reject H0. Right? See, you have the same answer. Right? So let's quickly do the two-sided test also. Right? In the two-sided test, how to get the p-value. Okay. Now it is a two-sided test. So you have to have the p-values from both tails. What is the test statistic? 1.67. It is positive 1.67, but when you find the p-value, you have to use both positive and negative 1.67. Okay, so addition of these two will be your p-value, right? Because of the symmetry, if you find this value, you can multiply it by 2, right? So it's the same thing because of the symmetry. So let's read negative 1.67 because that's easy. Okay, so can you find it for me? Negative 1.67. Negative 1.67. So the left tail probability is 0.04746. Very good. So you have 0.04746. So let's use it here. So one side is 0.04746. So what is your p-value? It's twice that number. Why? Because you have to add this tail also. By symmetry, it is also 0.04746. So what is your p-value? Yeah. Can you find the p-value? Multiply it by 2. Yes, the positive the positive 1.67 is 0.95254. Right, but what you want is the right tail, so you have to do 1 minus that, and you will get 0.04747. Okay. So if you multiply this by 2, what is your p-value? This will be 0.09492. Am I correct? Twice the p-value is 0.09492. Okay. Yes, Agnes, you got it correctly. And what is our alpha? Let's go back. It's 1%. So alpha is 1% is 0.01. Now what is the sign? 0.09 and 0.01. Greater than or less than? 0.09 is, well, this bigger than 0.01. So you fail to reject H0, right? See, it's the same answer. Okay, so I don't know which one will be easier for you. It depends from person to person, right? If you prefer the rejection region approach, you can continue with that. If you'd like to do the p-value approach, that's also fine with you, right? So either way, you'll get the same answer. And again, with the two-sided test for proportion also, you can double check your answer with the corresponding confidence interval, right? Here also, if alpha is 1%, your 99% confidence interval shall be constructed. Okay. The corresponding confidence interval. If you have 1% alpha, it will be the 99% confidence interval, right? P hat plus or minus. Z score for 99% is, we use 2.575, right? And what is the, this is what you use as the standard error, okay, what you have at the bottom, right? So let's do it. P hat is 0.65, no, P hat is 0.686. Plus or minus 2.575. Okay. And what is P naught? Now you have to use P naught, which is 0.65. 1 minus 0.65 divided by the sample size 490. So this will give you the 99% confidence interval, right? So find it. And how do you double check? Go back and get the P naught or the proportion you see under the null hypothesis, that is 0.65, and check whether 0.65 is included in this interval or not. Right now, this is failing to reject H0, so it should be inside this interval actually. Right, so that is why you fail to reject H0. Okay, so can you try this one? Find the confidence interval and double check your answer. Okay. Right. So now you know the critical value approach and also the p-value approach. Okay. So that is about the one sample hypothesis testing. Do you have any other questions before we move on to two samples? Any questions? Okay, everything clear? Right. So let's move on to the two sample t-test, the two sample hypothesis testing. So that is the second part of the chapter 6, hypothesis testing on two samples. Okay. Now, when we consider two samples, there can be different types of two samples, right? One is the independent samples. The two samples are independent. The other one is the dependent samples. Okay. So independent samples means now when you do hypothesis testing on two samples, what we are going to do is we are going to compare two populations. Okay, so here what we are going to do is we are going to compare two populations. Can be the proportion, it can be the mean, but we are going to compare the two populations, whether the averages are equal or not, whether the average of first population is bigger than the second one, whether the proportion of the first population is smaller than the second one. Likewise, we are going to compare these two proportions based on the average or based on the proportion. So when you are going to compare these two populations, either they can be independent or they can be dependent. Now, depending on whether you are comparing two independent samples or two dependent samples, the test statistic and the variability, the standard error you are going to use, they are going to be different. Okay. So when do we have independent samples? Now you know what is independence. You have done probability, independent events. You have done variables, independent variables, right? So what is the idea of independent populations? If you think about the usual context, the idea of independency. When do we say two populations are independent? So when you measure a certain measurement, the measurements of one population, it's not going to affect the measurement of the other population. Then we say the two populations are independent. Okay. So when you have independent populations, we'll say the behavior, you may say the measurements of one population does not affect or does not depend on, okay, the measurements of the second population. So for example, think about you are going to compare some clinical measurements of set of patients in a clinic in Kandy Hospital and another set of same type of patients, similar health conditions. There's measurements of some of the medical measurements in a clinic in, let's say, Anuradhapura Hospital, right? So you have a separate set of patients attending the Kandy clinic. You have a separate set of patients attending the Anuradhapura clinic. So they are not interacting with each other. So they are two independent samples, right? Say you want to compare, let's say, a simple one, compare the blood sugar levels, let's say. You want to compare the blood sugar levels of diabetic patients, let's say registered in Kandy clinic and Anuradhapura clinic, right? So you want to test whether if you compare these, the population of diabetic patients in Kandy clinic, so you can assume they are coming from around Kandy area and Anuradhapura, that north central area, whether the behavior is different, whether the diabetic patients in Anuradhapura having higher levels than Kandy or lower levels, or whether there's actually no different. So something like that you can compare. Now these are two independent samples. Can any one of you give me a different example for independent samples? Maybe you can use example from your context, from your radiography or radiology. Any example that you can give me for independent samples? Anybody who can try? It's okay. I can, define your answer if it is different. Weights of students in 2 universities. Yes, very good. That's one good example. Weight of students in 2 universities. Yes, you don't have any relationship between these 2 groups. Yes, that is 2 independent samples. Okay, any other examples? The rejecting the X-ray films in 2 hospitals. You mean the proportion of rejected X-ray films? I guess, right? The proportion of X-ray rejections, right? The proportion of rejected X-ray films in 2 hospitals. Yes, that's a very good one. So you can compare whether the rejection proportions are higher in one hospital or another hospital if the radiographers who are working there are not the same persons, right? So they are working independently. So that's okay. So that's a good example for proportion. Good. Any other examples? Male and female death comparison for COVID-19. Okay. So if you know for sure that the death does not depend on the gender, yes, you can do that. Okay, you want to so the male group and the female group, they should be independently selected, not the husband and wife of the family. Okay, likewise, so when you select the males and females of deaths, they should not be from the same same family, otherwise it can make a conflict. Okay, but if you consider as a whole all the deaths, right, then you can apply that. Yes, so let's write few of these examples you gave me. Proportion of rejected X-ray films in 2 hospitals. Proportion of deaths of males and females COVID-19. So likewise, you can come up with independent samples. Okay, thanks for the answers. Now, what about the dependent samples? When we talk about dependent samples, again, we have 2 different types. You can say matched pairs. Okay, and the other one is the pre and post measurements, right? So what are these matched pairs? You know, there are several studies that you do with people, or let's say human beings, where they are matched, right? One good example is the twin studies. Think about the twin studies. Now, suppose you want to find the survival pattern of twins, the first sibling and the second sibling. You know, usually if you have identical twins, they have very similar health backgrounds, right? They are maybe the life expectancies are very similar. If they have a certain disease, there's high chance that both of them will have the same disease. Okay, and any deficiency that they have, both of them will end up with that. So when you do twin studies, most often you end up with the behavior of one sibling, it affects the behavior of the other sibling. Okay, so that has been proven. So twin studies are matched pairs. You can't say the behavior of one sibling is completely different than the other sibling. Okay, so when, especially with the identical twins, they are going to be matched pairs. And another one is the husband and wife studies. Right, so they are also, now it depends on the objective of the study and the topic of the study. Say for example, the satisfaction about the income. Okay, so when you think about a family, both husband and wife, they contribute in some way. So depending on the way both of them, their behaviors will be combinedly affect the question. Okay, so the income of the family. So husband and wife studies, those are going to be matched pairs. You can't say the answer given by husband is completely different or has no effect on the answer from the wife according to their depending on their income. So they are going to be matched pairs. Okay, and sometimes you plan the matched pairs. Say for example, you do a certain study you find two patients, they have very similar medical history, similar in age, similar in gender. Okay, so there also you can come up with matched pairs analysis, right? And what about the organs in human bodies? The kidney, left and right kidney, eyes, again left and right eyes. They are, they are working together, right? If one eye fails, it affects the sight of the other eye. And usually if you think about the glaucoma and things like that, if one eye got affected, there's high chance the other one got affected. So they work together. These are dependent entities, the kidneys, lungs, eyes, even the hands and feet, the coordination, they are dependent for a certain one patient, one person, right? So they are also matched pairs. So if you are going to compare let's say think about a CKD patient, survival of the kidneys, left and the right kidney, obviously they are going to be depending on each other, right? So they are going to be matched pairs, and you have to use statistical test developed for matched pairs. Okay. The next one is called the pre-post measurement, right? Pre-post measurement is, I'll give you an example. Now, if you want to find the effectiveness of a certain workshop, effectiveness of, let's say, a mathematics workshop for non-mathematics major students, right? So why are you doing a workshop? To improve the mathematics knowledge, right? Now, if this workshop is actually effective, right? So the knowledge that the students had before they follow the workshop and then the knowledge they gained after the workshop, they should be different, right? Now, how do you check it? You can use a pre-post test, right? So what you do is you give a pre-test. You give a test containing some mathematical calculations to the participants, right? So you give a pre-test to the participants and grade it and find the scores. And you conduct the workshop, and at the end of the workshop, you give another test. We call it the post test. So this is the end of the workshop. You give the post test. Now it will not be the same test, but maybe very similar examples, very similar questions, right? Now, to whom are you going to give it? To the same participant, the same participants, right? So it's the same set giving you measurements before and after an in-between event, okay? So you take the exam scores or mathematics scores before the workshop and after the workshop for the same set of participants. So these are called actually before and after studies, right? Now, what if the workshop is effective? What should happen? The post-test scores should be considerably higher than the pre-test, right? So that means they have gained some knowledge from the workshop. Now their performance is higher compared to the pre-test, right? So those are called pre-post measurements. They are also dependent. Why? You have the same set of participants, same set of patients or same set of participants answering or giving you measurements before and after a certain event. Can you come up with another example related to biological sciences or area related to you? You can compare a treatment, how effective it is, right? Something like that, or a medication. Can you come up with another example? Okay, so checking the progress of a fracture before and after the fixation. Okay, so that's a very good one. So that means using an X-ray, right? So use an X-ray at the beginning of the fracture and then you do the fixing maybe after 1 month, and you take another X-ray and so you can compare the two X-rays. Yes, that is a very good example. So let's say checking the progress of before and after. fixation. So I have another one. Comparison of weight after a fitness program. Yes, that's a very common place where you can use pre and post. Comparison of weight after a fitness campaign. So let's say weight loss, weight losing campaign. So if the campaign is good, they should their weight should be decreased, right? So you measure the weights of the participants before the campaign, then you conduct the campaign, and at the end of the campaign, you measure the weights. So if they did the campaign correctly, their weight should be reduced, right? So you have another one from Sashini, cancer treatment for a patient and analyzing the size of malignant tumor using an X-ray. Okay, so that's another one. So before the treatment, you use the X-ray to measure the tumor, and then after the treatment, you measure it again, same patients, and see whether it is reduced or not, right? Or I don't know, so the behavior of it, whether it is decreased after the treatment. Okay, so those are very good examples. So let's write that also, comparing weights from a fitness program. So again, it is a before and after, and then cancer treatment, affecting tumor. So again, before and after, right? So those are very good examples, right? So these are the dependent samples. Okay, again, you can test using hypothesis whether there is a significant difference in the post measurements and the pre-measurement, right? Okay, so that's what we are going to cover under this two sample test, right? So let's start with the proportion as usual. We are going to compare two independent proportions. Okay, so let's start with the independent samples first, and then let's move on to the dependent samples, right? Now, there is a difference in writing the hypothesis, right? Now you have two proportions. So let's say proportion 1 and proportion 2. So this is from population 1. Proportion 2 is for the population 2. And you take a sample from the first population, and you take a sample from the second population. So you have p hat 2 and p hat 1. So those are the estimates, right? So you're going to use them. So this is the population size. Let's say N1 and N2 may be same. It doesn't matter. You can have different sample sizes, different population sizes. That's fine with the independent samples. Okay, so but it's not going to be same with the dependent, right? When you have matched pairs, you have to have the same number in both groups. Pre-post measurements, same number of participants. If there are 20 participants in the workshop, you need 20 tests, 20 pre-test scores and 20 post-test scores. Same sample size. But with independent samples, you can have different sample size. They are not going to affect because they are independent, right? Now, how do you write the hypothesis? You know, there's going to be three different alternatives, two-sided, left side and the right side. So this is how you write it. Okay, let's start with the two-sided test. Here's my H0 versus HA. Now we are comparing two proportions. Okay, so you can do it in two ways. P1 minus P2 equals 0. That is, the difference is equal to 0. That means there is no difference. Or P1 minus P2 not equal to 0. Okay, so that is one way to write it, or you can write it like this: P1 equals P2 versus P1 not equal P2. That is the two-sided test. Now, can you remember how we wrote the hypothesis for one sample? We had a number, right? We had a number P1 equals a certain number, P equals 0.5, P equals 0.65, something like that. Now what do we have? We have two proportions. We are comparing two populations. So you have two proportions, okay? So shall we try the right side test? P1 minus P2 less than or equal to 0 versus HA P1 minus P2 greater than 0. So this is the right side test or right tail test. Or the other way is P1 less than or equal P2, P1 greater than P2. We usually go with the first one. I'll recommend the first one because if you use a software, that is how you get the output. Okay, so it's good if you stick with one. Right? Now you can guess what will happen in the left tail test. P1 minus P2 is less than 0. Okay. Since you have the idea about hypothesis now, it's only changing the letters, right, to accommodate two population. Okay. So let's do an example. Okay, so you have 800 participants where 605 are from non-smokers, 195 are from a smoking group. And a question was asked from these participants. What is the question? Should the federal tax, let's say the government tax, on cigarette be raised to pay for the health care? Okay, so a certain controversial question anyway. Should the tax on cigarettes be raised so you can pay for the health care? So when you ask this question from non-smokers and smokers, okay, so let's see whether their opinions are same or not. So what do you have to test? Is there sufficient evidence at 5% alpha to conclude that the two groups differ with respect to their opinion? So what is the opinion? Whether the tax should be increased so you can pay the health care bill. So these are the results. Okay, so you have the non-smoking group and you have the smoking group. So what are the total values? Let's say N1 non-smokers 605, smokers 195. Okay, and the number who said yes, that number is 351, and out of the smokers only 41 said yes, right? So out of 605, 351 said yes. Out of smokers of 195, 41 said yes, you have to increase the tax to pay the health care. Now we are going to check whether this opinion of yes is same or different in these two groups. So it says differ with respect to the opinion. So what is it? What side of a test is that? If you are checking whether there is a difference, it is going to be the two-sided test, equal or not, differ. Right? So shall we write the hypothesis? Okay, can you first find the P1 hat and P2 hat? Because we need that. How do you find P1 hat? 351 divided by 605. P2 hat 41 divided by 195. So find these values. You will need it when you find the test statistic. Okay, right. So let's write the hypothesis. So I'm using non-smokers as one group and smokers as the second group. Okay, so we have P1 minus P2 equals 0 versus HA P1 minus P2 not equal 0. So I assume that you are also doing this work with me using your notes or papers. Just don't sit and look, right? So try these numbers, see questions, okay, with me, follow me. So then it will be very easy to understand, okay? Don't just sit and watch. Do these calculations with me, okay? Right. So this is our hypothesis, two-sided test. Why it is two-sided again? Because you are going to check whether their opinion differs, not equal, right? Now, what is the next step? You need the test statistic, right? So here's the equation for the test statistic. Again, you don't have to memorize them, as I always mention. It will be provided. May I write the test statistic somewhere here so you can use it with the other calculations? Sorry. Here's the test statistic. Always it is going to be a z-score, you know that, with the proportions p1 minus p2 hat. We use minus 0 because we are, as I said, we are always using this first one. That's the recommended one. And what you see after the sign is 0, right? What you see after the sign is always 0. So that is why we have this 0 here. Okay, that is what you see under the null hypothesis. And here's your standard error, right? So look at this standard error. You have p hat 1 minus p hat times 1 over n1 plus 1 over n2. Okay. So what is this p hat? This is called the pooled estimate, right? That means you combine these two groups together, okay, and find the pooled estimate. So this is called the pooled estimate. That means both smokers and non-smokers, you combine together and find the total number of users. That will go in your test statistic. Okay, so let's use it here. So I'll write the test statistic again. P1 hat minus P2 hat minus 0. Pooled estimate 1 over n1 plus 1 over n2. Right. Okay, so find P1 hat and P2 hat. I asked you to find it. Can you tell me what is P1 hat and P2 hat? P1 hat, P2 hat, and then let's find P hat also. So what are x1 and x2? Those are the responses, right? How many said yes? So in this case, it's 351 plus 41 divided by sample size is 605 plus 195. Okay, so we have P1 hat is 0.58, thanks. And P2 hat is 0.21, okay, that's correct. And what about the pooled estimate, P hat? This is 392 divided by 800. Let's find the P hat also. So then you have everything you need to find the test statistic. Okay, so that is 0.49, yes, correct. Right, so we have everything we need now. Shall we find the test statistic? P1 hat is 0.58 minus 0.21 and minus 0, so you can omit writing it if you want. The square root is for everything. Okay, be careful, the square root is for everything. P hat is 0.49. 1 minus P hat is 1 minus 0.49 is 0.51. 1 over, what is N1? 605 plus 1 over 195. Whole thing square root. Right, so be careful when you plug in these values to the calculator. So what is this? Is the test statistic? It's always going to be an Z score, right? With the proportion, it's always an Z score. Okay, so can someone tell me the test statistic? Okay, so the test statistic is it should be a smaller value than 218. Did you miss the square root? Okay, so here's what I got. It's 8.99. Okay, so you got 9.0, so that's okay. So let's go for 9, right? Due to rounding errors, you made that. So let's say it's 9. Anyway, we said score 9. That's a very large number, so it doesn't matter. 8.99 or 9.1. Okay, it's 9.02. Right. So let's say it's 9, right? So let's use the rejection region approach. Sorry, the critical value approach. So you have two-sided tests, which means you have rejection regions on both sides. What is the alpha? At 5% alpha. So you have to divide 5% by 2 and put 1/2 to the left and 1/2 to the other. With 5%, you already know the boundary will be 1.96 plus or minus, right? You already know for tail probabilities 2.5%, it is going to be plus or minus 1.96. Okay. And it's very, very clear that the Z score 9 is far, far away in the tail somewhere here. So this is, let's write the decision. Since the test statistic is in the rejection region, if we reject H0. Okay, so you can write the conclusion. How do you write it? We can conclude at 5% significant level. What can you conclude? So you reject H0. You rejected this. That means you can conclude your HA. What is HA? PA is not equal to P2. That means their opinions are different. Level that. The opinion is different between the two groups. Let's say smokers and non-smokers. Right? So since you know the idea about the hypothesis testing, the test statistic, and how to make the conclusion, everything, it's the same thing. The difference is now we are doing it for two populations with a new equation. That's it. All the other steps, the things, the procedure, it's the same thing. Okay. Is this clear to all of you? Any questions? Let's do one more example from proportion. Right, it's 330. Hope I can do the mean also. Right. Okay, so shall we move on to the next example? Right. A researcher wants to test the effectiveness of a new anti-anxiety medication. In a testing 64 out of 200 taking the medication reported symptoms, and you have a control group, which is the placebo group. 92 out of 200 reported symptoms. So can you conclude that the medication is working better than the placebo? Placebo means, do you know what placebo medication is? What is placebo? Yes, what is placebo? Have you heard this earlier? Placebo is a medication used with control groups, usually in pharmaceutical clinical trials. Suppose you have a drug that you want to test its effectiveness or something. So you have a set of two sets of, let's say, participants. You give the drug to one set, and the others you can't just give nothing, because they will think we didn't get any, the mental situation can harm the outcome. In order to reduce that, for them also they give a drug. That drug is called the placebo. It's actually doing nothing. Okay, it's not doing anything, just that, but the participants think that they got the drug. Okay, they got the pill. So then you compare the maybe after a certain number of hours, the symptoms or behavior or any other measurement, you check it between the two groups. So if the medication is working, it should give different findings than the control group, right? Control group, they got nothing actually, although they think they got a medication, the placebo, that actually placebo is doing nothing. Okay, so that is usually what we used in control studies, right? So you have two different samples, 200 who got the medication, 200 who didn't get. Okay, and then you compare whether they got the symptoms again, the anxiety symptoms. So if the drug is good, after taking the drug, the symptoms should not occur or less occurrence, right? So let's check it. We are going to check whether the medication is working better than the placebo. So let's see how we can write it. So I'll say, let's name them P1 and P2. If you want, you can use PA, PB, okay, things like that, right? So let's say P1 is for the medication group and P2 is the placebo group, okay? Now, if the medication is working better, what do you think about the proportion of participants who got the symptom? If the medication is working better, the proportion of symptoms should it be larger or smaller? That proportion should be greater or less? What do you think? So you have to argue a little. Yes, it should be smaller, right? If the medication is working, if the medication is actually working, the proportion who got the symptom should be lowered, right? Compared to the others who didn't get the medication. So therefore, what you want to conclude, can you conclude it is working better, right? So what you want to conclude should go to HA. So let's fill HA first. Then let's do the opposite. What should be SA? The medication is working better. The proportion of people who got the symptom should be less than the proportion from the placebo group, right? So this should happen. So how do you write it? P1 minus P2 should be capital P, because we are writing the population values in hypothesis should be less than 0. So what is the other one? P1 minus P2 should be greater than or equal to 0. So this is going to be a left tail test. Is this clear how you figure out the HA? Because you want to conclude that the medication is working better. If it is working better, the proportion who got the symptom should be less than the placebo group. So it should be P1 less than P2. So you write it like this. Okay. Now the first thing, let's find what we want. Find P1 hat, find P2 hat, and also the pooled estimate. Okay, so let's do it together. P1 hat, this will be 64 out of 200. Okay, so you'll find it is 0.32. P2 hat is 92 out of 200. Proportion is 0.46. So this will be 64 plus 92 over 400, which is 0.39. Right, so let's write the test statistic. It's going to be z-score, P1 hat minus P2 hat minus 0 divided by the pooled estimate and the sample sizes. Right, so we have 0.32 minus 0.46 divided by 0.39. 1 minus 0.39 is what is it? 61. 1 over 200 plus 1 over 200 again. Okay. If you do that, your answer will be, see, it is going to be negative 0.32 minus 0.46, so it's going to be negative 2.869, right? So that is our test statistic. Okay, so let's use the, shall we do the p-value approach? Let's use the p-value approach. Let's find the p-value. So this is going to be a left tail test. Our test statistic is negative 2.869, so we can go for 2.87. Let's read the table and find this p-value, and then you have to compare the p-value with alpha. Okay. So shall we look at the negative 2.87? Can you find that tail probability? Negative 2.87 is its score. Okay, so I have the p-value, one answer, let's see. That is going to be 0.00205. Hasini, that's correct. Can all of you get that number for negative 2.87? It's 0.00205. 0.00205. Okay, now let's compare it. What is our alpha? Can you conclude at 5% alpha? 5%, 0.05. So see, you can see that this is a very small number, which is going to be the less than. Okay, if the p-value is less than alpha, that means we reject H0. That is the rule. If p-value is less than your alpha value, we reject H0. So what is your conclusion? You can actually conclude that the proportion who got the medication is less than the placebo group, which means the medication is working better than placebo, or this medication is actually effective. Is that clear? So reject H0, that means the proportion of symptoms who got the medication is lower than the placebo group. That means the medication is actually working properly, or it is effective. So we can say, we can conclude at 5% significant level, let's say the medication is effective, or I can say medication lower the symptoms, right? So that is how you do the comparison. Similarly, you can do a right side test also, right? Depending on the context. Now you know how to do it. You'll end up with a right tail test, a positive test statistic, and well, either using p-value approach or the critical value approach, you can make the decision. Okay, right. Shall we move on to the means? Again, it's the same thing. Now you replace your hypothesis with, instead of proportion, you use mu, and then depending on the case 1, 2, or 3, you have the corresponding test statistic, and the rest is the same. Okay, so I'll explain the hypothesis quickly. The two independent means, again, we have population 1, population 2, having mean mu1 and mu2. You take a sample, you have x1 bar and x2 bar, and you are going to compare the two populations using the sample means. Okay, right. So how will your hypothesis look like? mu1 minus mu2 equals 0 versus HA mu1 minus mu2 not equal to 0. So that is the two-sided test. Right side test. Sorry. Right side test, and then the left side or left tail test. Okay. Now remember, with the mean we have something extra about the cases, right? Case 1, sigma 1 and sigma 2 known. Okay, so both should be known, right? If at least one is unknown, well, you have to go for a third case, right? If sigma 1 and sigma 2 both are known, you'll end up with the Z curve. And what we see here is 0, so I'll write 0. It's very similar to the proportions test. And here's the standard error. Into, okay. What is case 2? Sigma unknown. Both N1 and N2 large enough. Okay, both of them. If one is very small sample size and the other one is large, still you have to go for case 3, right? Because with the smaller sample size, you can't assume the normal distribution. Okay. So in order to use case 2, if you do not know sigma, both sample sizes should be large enough. Then only you can use the Z score. Again, this is going to be the same thing, but replace sigma with what? S1 square. That is the sample standard deviation. The case 3, I'll write it separately because in case 3, what happens is sigma unknown, n small. I'll just write n small. That means at least one. Okay, maybe n is large, n1 is large, but n2 is small. Still, you have to go for this case. Then you'll have a t score. Your test statistic is going to be similar to the, this is the minus sign. Okay. Right, this is the one. This will follow a t distribution with degrees of freedom. I'll use mu because since you have two sample sizes now, the degrees of freedom, it's going to be a certain equation or approximation that you have to use. An alternative way is to use the mu as the minimum of n1 minus 1 and n2 minus 1. Okay, that's a like a shortcut, or whenever you have no other option, you can go for this. But actually, the degrees of freedom mu will be calculated using this equation. This is called the Strathers weight formula. If you use a computer or a software, a statistical software, this is the degrees of freedom it will calculate, and according to that, sorry, I'm using two different notations in one. So again, you don't have to memorize these things, okay? Don't have to memorize, just know that this is how they are calculated. If you use a statistical software, the degrees of freedom will be calculated using this Strathers weight formula. And according to that, a p-value will be given. So you don't have to worry at all. You look at the p-value and make the decision. Okay, but if you do it by hand, if you want, you can go for this minimum, or usually the degrees of freedom I provide it to you in examinations. the degrees of freedom will be given to you. Okay, so you don't have to worry about doing these lengthy calculations. Okay, I gave this equation just to complete this notes. Okay, so you know that this is what actually happens when you calculate the p-value. Okay, right. So this is the test statistic. You know the hypothesis. The rest is the same. Right? You just apply it and make the conclusion. Okay. So shall we do the example very quickly? So here's the example. A mathematics test was given to 2 classes to test the performance of students of 2 colleges. Okay. So you are going to compare the performance of students in 2 colleges, right? So that is your population. You are going to compare it based on a sample. What is your sample? You have selected 2 classes from college 1 and also from college 2. Okay. So suppose these are the summary information. This is the college 1 and 2. The sample sizes. Now they have different sample sizes, and 1 is 20 and 2 is 15. That's possible, right? When you have independent samples, you can have different sample sizes. Then these are the sample means. X1 bar is 75.8 and X2 bar is 76.2, very close. And the sample standard deviations, S1 is 2.68, S2 is 1.25. Now there's a difference between the deviation. Okay. So now what do you have to do? Test whether the performance differ between the 2 colleges at 10% alpha level. Okay, so shall we do this one? What is the first thing you have to do? Look at the information and see whether it is case 1, 2, or 3. Do you know sigma? You don't know sigma. What you know is the sample standard deviation, S1 and S2. So sigma unknown, now look at the sample sizes. 1 is 20, 1 is 15, so both are small. So this is going to be the third case, right? So you know how to find it. Very good. Okay, and what side of test is this? Test whether the performance differ. Differ means not equal. So you're going to compare whether the performance are equal or not. So shall we write the hypothesis? Do it with me. Mu1 minus mu2 equals 0 versus mu1 minus mu2 not equal to 0. So you have the two-sided test. Now let's find the test statistic. So this is the third case. It's going to be a t-score. Let's use capital T here. It will be x1 minus, x1 bar minus x2 bar. S1 square over n1 plus s2 square over n2. Right, so let's find it. 75.8 minus 76.2 divided by S1 is given, so you have to square it. S1 square 2.68 square over 20. Now you don't square 20, okay? See, just n1. Now sometimes they will give you S1 square sample variance. So be careful when you plug in the values, okay? Check whether what's given is S or S square. Here it is S, so you have to square it. And 2 is 15. This follows T distribution with the degrees of freedom mu. And I'll give you this. It's going to be 28. Okay. So I used that formula and found that the degrees of freedom is 28. Okay. So let's use it. So what is the test statistic? If you do this calculation, you will end up with negative 0.587. So please do the calculation and check whether you can get the same answer, right? Negative 0.587, right? Now let's find the rejection region because it's T. You can't use the p-value approach. So the rejection region is going to be on both sides because it is a two-sided test. And what are the critical values? We have to test at 10% significance level. If your alpha is 10%, each tail will contain half of it, 5% and 5%. With degrees of freedom, 28. Okay, shall we check the t distribution? Okay, again, degrees of freedom 28. The tails will contain 5%. Right, so let's check the t distribution. One tail should contain 5%, 0.05. That's with the 90% confidence, or 10% alpha means 90% confidence interval. So one tail contains 0.05, the degrees of freedom 28. So there you go. The t-score is 1.701. Okay. T-score is 1.701. So what is that t-score? The critical value of the rejection region. Negative and positive according to the symmetry of the t distribution. So here's your rejection region. Now what do? You go back and get the test statistic and place it on the graph. Now where is it? 0.5 should be somewhere here, right? Negative 0.587. So what is your conclusion? Test statistic is in the non-rejection region. So what happens? We fail to reject H0. Okay, we fail to reject H0. So what is your conclusion? If you fail to reject H0, you can't conclude this, right? So you cannot say that actually there is a difference, right? So you cannot conclude that average of the first one is not equal to the second one. Okay, because you fail to reject H0, you cannot conclude what you wanted. So we say we do not have enough evidence to conclude at 10% significant level that the performances, let's say the performance different between two colleges. Okay, maybe if you take another sample, larger sample with a different alpha level, you will be able to reject it. But with this sample, we were unable to do that. So we do not have enough evidence to say that there is a difference. Okay. Any question from this example? Is this clear to all of you? The steps, calculation, decision, and everything? So it will be very effective if I could have done this in a lab session, showing the compute output also, and show you how these test statistics and everything tally with your answers, right? But unfortunately, we cannot do at this time. But I'm hoping we will get at least 1 or 2 lab sessions to cover all these practicals, okay? Right, so that's the independent samples, right? So next will be the dependent samples, but we don't have enough time, only 7 minutes. So I'm going to stop for today. Do you have any questions before we wind up for today? Is everything clear to you? I hope I'm not too fast. So I will be uploading the video and also the notes. So make sure you refer them, okay, and understand. And whenever you come to the next class, if you have any place unclear, let me know so we can clarify it before we move on to the next topic. Okay. No questions? Okay, then let's stop for today. And I'll make sure to upload the notes and the recording to your LMS.